Hello and welcome to another video on orbital mechanics. I'm going through the book Orbital Mechanics for Engineering Students by Howard D. Curtis. It's been a while since I did one of these because I've been quite busy starting a new job, and I was maybe going to skip over some of these, but I've decided not to, just to get the practice. So the next problem on the list is 2.20, and if you've been following along or doing any of this book up to this point, you should be getting pretty good at solving these problems. And this one is just a simple input of data into the equations. So the question is, an unmanned satellite orbits the Earth with a perigee radius of 10,000 kilometers here. And an apogee of 100,000 kilometers. And it wants us to calculate 7 different terms. The first one is the eccentricity of the orbit, right? So, but first we're going to get the semi-major axis A, and we're going to get that just with a simple equation of rp plus ra over 2, right? And that equals 55,000 kilometers. That's the semi-major axis. And then we can get the eccentricity from that, because there is another very simple equation which is a simplification at theta equals 0, rp over a, 1 minus r, the perigee radius divided by the semi-major axis, and that gives us 0.8182. So that's part A, and then part B is the semi-major axis. Part C is the period of the orbit. So to get the period of the orbit, we are doing 2 pi AB over the angular momentum, and the angular momentum equals the square root of, this is another rp plus, this is a rearranging of another equation, times E times the gravitational constant. So this one is, I think it's a rearrangement of, rp equals h squared over gravitational constant 1 over 1 plus e. So we have that, and we have that, and we have that. So we rearrange, we get this, and then input into there, t comes out to be 35.66 hours. And then part D, the specific energy of the orbit. So that is, again, let's see, it's I've done this in a couple of different ways to confirm. Not all the answers are provided in the book. So I have got minus a half times squared divided by h squared minus e squared. If you go back to the elliptical orbits video that I did, you'll see this does come out in the process. So you can use that one. You can also use half times h squared over rp squared minus mu over rp. So there's another one that you can use. Yeah, that's also in that elliptical orbits video. And then the other one is velocity at perigee over 2 minus mu over rp. You can also use that one. So all of these can be used, and they're all just variations of different equations that we have come across throughout the process, and they all equal minus 3.62 by 10 to the 6. That is megajoules per kilogram, or kilometers squared per second squared. Assume these convert between each other exactly the same. And then E is the true anomaly at which the altitude is 10,000 kilometers. So to get the true anomaly at 10,000 kilometers altitude, new cos inverse 1 minus e squared times a over r minus 1 divided by e. And this is again an equation that is being rearranged. Right. If you there are, this one's coming from this one, r equals a 1 minus e squared or 1 plus e cos theta. So we're rearranging that. So r in this case though is equals the radius of the Earth plus the altitude. Which is 16371 kilometers. So in the question it's 10. The altitude is 10,000 and the radius is 6371 kilometers. So total is that. Plug in r and rearrange the equation. Plug in our other values. Theta equals 82.23 degrees. And then F is asking for the velocity radial and velocity azimuth at the points found in part E. And there are two equations for this. So the azimuth equals mu over h one e sine theta, and velocity radial equals mu over h times 1 plus e cos theta. that equals 3.8 kilometers per second, and that one equals 5.2 kilometers per second. And then the speed at perigee and apogee for part G. It's a bit of a strange one to finish on, to be honest. And so we can just get that with the velocity formula. It's v square root of mu over 2 over r minus 1 over a. And do it for perigee and apogee, you'll get, you get what's in the book. Straightforward enough. Of velocity at perigee equals 8.5 kilometers per second, and velocity apogee equals 0.85 kilometers per second. Yeah, so it really is just plugging in the numbers and rearranging equations. If you've followed my other videos, this should be straightforward. If you think I've made a mistake, let me know. If you have any questions, put them in the comments, and I will put the MATLAB script in the description as well. Thank you very much. Bye bye.